Charles Steinmetz. 4 Lectures on Relativity and Space. 1923. All books on my channel are in public domain. Please subscribe. If you like it, please give thumbs up, share and comment. C. Relativity of length and duration. What does this mean? The train stands on the track. I measure it from the outside, you measure it from the inside, and we find the same length. We compare our watches and find them to go alike. Now the train starts and runs at high speed. While it is passing me, I measure its length again and find it shorter than before, while at the same time, you, traveling with a train, measure it again from the inside and find the same length we both found when the train was standing still. But while passing over it, you measure a piece of the track and find it shorter than I find it when measuring it from the outside. While you pass me on the train, I compare your watch with mine and find your watch slower than mine. But, at the same time, you, comparing your watch with mine, while passing me, find my watch slower. Then the train stops, and both our measurements agree again. What then is the true length of the train and the true time, that which I get when measuring the train while it passes me at high speed, or that which you get while moving with the train? Both, and neither. It means that length is not a fixed and invariable property of a body, but depends on the condition under which it is observed. The train has one length to the observer standing still with regard to it, that is, the observer in the train, a different and a shorter length to the observer whom it passes at 100 feet per second. And if I could go outside of the Earth and measure the length of the train, while the train and Earth rush by me at 20 miles per second, I would find a third still shorter length. Length and time, therefore, are relative properties of things, depending on the conditions under which they are observed, particularly the relative speed of the body to the observer. This really is so startling only because it is novel, since at all speeds which we find around us, even the highest speeds of rifle bullets, the change of length and time is so extremely small as to be inappreciable, and we therefore are used to finding length and time constant. Appreciable changes occur only at the speed of 10,000 to 100,000 miles per second. While the most accurate methods of measurement would fail to show an appreciable shortening of the railway train going at 60 miles per hour, because the shortening is so small. But it is there just the same. However, the relativity of the length of a body, that is, the dependence of the length on the conditions of observation, is no more strange than the relativity of the color of a body. Offhand we will say that a body has a fixed and definite color. The grass is green, the snow is white. Nevertheless, when we think of it we know it is not so. The lady buying material for a dress in the dry goods store during the daytime may select a nice heliotrope. But when the dress is finished, in the ballroom, she finds its color a clear soft pink. And when, to have a photograph taken, she goes to a photographer using mercury lamps in his studio, she finds the dress a clear blue. Which is its true color? Heliotrope, or pink, or blue? Any of the three is the true color in the condition under which it is observed. So, Einstein's theory of relativity proves to us, it is with length and with time. There is no single length of a body, nor time on the body, but length and time are relative and vary with the conditions under which they are observed, with the relative speed of the observer. Just as the color of a body varies with the kind of light under which it is seen. D. Relativity of mass. If, then, in a body moving rapidly past us, the distance appears shortened and the time slowed down, the speed, which is distance divided by time, must also appear slower. Now, the energy of the moving body depends on its mass and its speed, and with the same energy put into the body, if the speed appears slower, the mass must appear larger. We thus draw the conclusion from Einstein's theory of relativity that the mass of a moving body is not constant, but increases with the speed, and the oldest of the great fundamental laws of nature. The law of conservation of matter, thus goes into the discard. For nearly 2 centuries we have accepted the law of conservation of matter and believed that matter, that is, mass, can neither be created nor destroyed. And now we find that mass varies with the speed, so that speed, that is, energy, can create mass, and mass or matter probably is merely a manifestation of energy. And this can be, and has been verified experimentally. The decrease of length, the slowing down of time, the increase of mass, becomes appreciable only at velocities approaching that of the light. Thus at ordinary everyday velocities length, time, and mass are constant. But in the vacuum tubes used in our big wireless stations to produce electrical vibrations which carry the message through space across oceans and continents, or to receive the faint signal arriving from far distant stations, the current is carried through the empty space of the tube by minute particles, so-called electrons. And measuring the speed and the mass of these electrons, the physicists find that they move at speeds of 10,000 and 100,000 miles per second and that their mass is not constant, but increases with the speed, in the manner required by Einstein's theory. This was the first experimental proof of the change of mass, and it was found before Einstein gave the explanation in his relativity theory. E. Acceleration and the law of gravitation. Suppose you have a billiard table in your house. You put a ball in the middle of the table. It stays there until something pushes it, and this something we call force. Or you shoot a ball across the billiard table. It moves in a straight line until it strikes the boundary, rebounds and again moves in a straight line at constant speed. Suppose now we have a billiard table in a train, and the train is running at constant speed on a straight level track. You again put a ball in the middle of the table and it stays there, just as was the case in your house, at rest with regard to the table, though I, standing outside near the track. See that train and table and ball all three move together at constant speed. You shoot the ball across the table, and it moves in a straight line at constant speed, thus in the moving railway train obeying the same law of nature as in your stationary house. The law that any body keeps the same state, whether rest or motion, until something changes its state. But suppose the train is speeding up, its speed increasing while you put the ball in the middle of the billiard table in the train. Now you find that this ball does not remain at rest, but it begins to move toward the back of the train. First slowly and then more and more rapidly until it comes to rest against the back boundary of the table, just as a stone which I drop does not remain at rest, suspended in the air, but begins to move downward with increasing speed, falls. So the billiard ball in the speeding train falls toward the back of the train. You shoot a ball across the billiard table while the train is speeding up. It does not move in a straight line, but curves toward the back of the train, just as a thrown stone, on earth, does not move in a straight line at constant speed, but curves downward. You say then that in the speeding railway train some force acts on the billiard ball, pulling it toward the back of the train, just as the attraction of the earth pulls downward. You may speculate on this force which attracts things toward the back of the speeding railway train and find its laws just as Newton found the laws governing the force of gravitation. But I, standing on the embankment, near the track, while the speeding railway train passes, see that there is no real force acting on the billiard ball, but when you put it in the middle of the table. Left to itself, it continues to move in a straight line at the speed which it and the train had when you put it there. What happens is that the billiard table and train, speeding up, slide forward under the ball, and the ball thus seems to fall backward toward the end of the train. So, when you shoot a ball across the billiard table in the speeding railway train, I from the outside see the ball move in a straight line at constant speed. But see billiard table and train slide forward under it, so giving you, who are moving with the speeding railway train, the impression of an attracting force pulling the ball toward the back of the train. You try to find the laws of this force, that is, the laws obeyed by the relative motion which you see. But to me these motions are those of a body left to itself, in a straight line at constant speed, and, knowing the motion of the speeding railway train, the mathematician can calculate the motion which you observe, without any physical assumption, merely as a mathematical transformation from the straight line motion which I see from the outside to the complicated motion relative to the speeding train which you observe. And so derive the law of the latter motion, that is, the law of the fictitious attracting force, to which you ascribe these motions. This Einstein has done, and so has derived a new and more general expression for the law of gravitation, in a way which does not depend on any hypothesis concerning the nature of the force. This law is more general than Newton's law of gravitation, and the latter appears as the first approximation of Einstein's law of gravitation. The more general law of gravitation given by Einstein does not mean that Newton's law of gravitation is wrong. Both laws give so nearly the same results in almost all cases, even in the calculation of cosmic motions, that usually the difference cannot be discovered even by the most accurate measurements. This is to say that Newton's law is a very close approximation of Einstein's. There are a few cases only in the universe as we know it today where the difference becomes noticeable. Such, for instance, is the motion of the planet Mercury. This planet has been observed for thousands of years, but all attempts to calculate its motion accurately by Newton's law have failed, while the application of Einstein's law has succeeded, thus once again corroborating his theory of relativity. To summarize the conclusions at which we have arrived, the theory of relativity means all phenomena of motion, space, and time are relative. The laws of nature, including the speed of light, are the same everywhere. From these principles it follows that length, time, and mass are relative also, are not fixed properties of things, but vary with the relative speed of the observer. A more general law of gravitation is derived as a mathematical transformation of straight-line inertial motion to the apparent motion relative to a speeding system, the railway train in above illustration, and shows that gravitation is not a real force, but a manifestation of inertia, just as centrifugal force is.